When you turn on your tap, water flows. Simple.
Right. Seems simple.
Or when firefighters need to tackle a blaze, they crack open a hydrant and, wow, water gushes with incredible force.
Huge pressure.
It's an everyday miracle, one you probably take completely for granted. I mean, most of us rarely, if ever, think about how that happened.
No, you just expect it to be there.
Exactly. It's just there.
Yeah.
But powering that miracle is a vast, intricate system. Pipes, pumps, towers, valves, this whole invisible machine quietly keeping our civilization alive.
Yeah, it nourishes pretty much every single aspect of modern life.
Yet it's designed to be unseen, unheard most of the time.
That's the goal.
Okay, let's unpack this then. In this deep dive, we're going to pull back the curtain on the water system. We'll explore this hidden infrastructure that, most people never see but rely on every single day.
And our mission today is really to give you a shortcut to being well-informed about this critical network. We'll break down its key components, reveal some of the ingenious design behind it, and explain why understanding this hidden lifeline is maybe more crucial than ever for you. We want to uncover some surprising facts, but without completely overwhelming you with technical details.
Sounds good. So where do we start? Maybe with something people actually do see sometimes, those water towers.
Yeah, perfect starting point.
We often see them as landmarks, right? Towering over towns. But what exactly are these hidden giants doing? What's their true purpose?
Well, fundamentally, water towers are elevated storage tanks. They hold potable water, sure, but maybe more importantly, they maintain consistent pressure throughout a distribution system.
Ah, okay. Pressure.
Exactly. Think of them as giant gravity-fed batteries for water pressure. It's clever engineering, really. They silently stabilize pressure across these huge networks and provide critical supply, especially during emergencies or power outages.
And they come in different shapes, don't they? I've seen the round ones that look like, well, like a Tin Man.
You have. There are various designs, yeah. The classic Tin Man style, those sleek, modern spheres, robust composite towers. Each is kind of optimized for aesthetics or capacity or maybe just the location.
So how does all that water actually get up there?
Yeah.
And how does it maintain this steady pressure without, constantly running pumps?
It's surprisingly simple physics, actually. Water is pumped into them during low demand period.
Like overnight?
Typically overnight, yeah. Then the sheer height of the tower creates significant gravity-fed pressure, around 0.43 psi per foot of elevation, roughly.
Okay.
So when demand rises, think morning showers, everyone getting ready for work, or, critically, during a fire, water simply flows out under its own weight, keeping the pressure steady across the system.
So it's a passive system in that sense.
Largely passive, yes, which means they're absolutely vital during emergencies like power outages. They act as a reserve of both water volume and pressure when the pumps might be down.
That makes sense. But there must be equipment involved too, not just the tank itself.
Oh, absolutely. There's essential supporting equipment. Booster pumps might help push water into the tower or maintain pressure in really large systems. Chemical pumps ensure treatment chemicals like chlorine or fluoride are evenly distributed.
Right.
And crucially, backup generators, they keep the pumps and control systems running if the main power goes out. Gotta keep those towers filling.
So it's not just a passive structure sitting there. There's active management involved. What's the role of the operators? Are people watching these things constantly?
Absolutely. Human operators play a critical role. They monitor water levels daily, often using advanced SCADA systems, supervisory control, and data acquisition, basically digital sensors and remote controls.
Okay.
Their job is to constantly balance supply and demand. They make sure towers are filled during off-peak hours, like we said, and then drawn down during peak times, usually morning and evening rushes.
So they don't run dry unexpectedly.
Exactly. You don't want the tanks to bottom out during a sudden surge in demand. That would cause pressure drops across the system. And this brings us to maintenance, which is where, the real vigilance comes in. These structures need routine internal and external inspections.
What are they looking for?
Sediment, biofilm, mineral buildup stuff that naturally accumulates. They need regular cleaning and painting specialized coatings. That's critical, not just for looks, but to prevent rust and control contamination. It's a constant battle against the elements, really.
Yeah, I can imagine. Steel and water.
Yeah.
constantly interacting. Corrosion must be a huge issue. How do they even fight that?
Right. That's where something really interesting called cathodic protection comes in.
Cathodic protection. Sounds technical.
It is a bit, but it's ingenious. It's essentially an electrical system that actively prevents the corrosion of the steel tank.
How does electricity stop rust?
Well, it uses either a small electric current or what's called a sacrificial anode, a piece of more easily corroded metal, to counteract the electrochemical process of rust. It basically makes the tank the cathode in an electrochemical cell, preventing it from corroding.
Wow.
Without it, these massive steel tanks, constantly wet, would rust through incredibly quickly. It's a silent, unseen defense mechanism against decay. But even with all that, issues still pop up. Corrosion is always a threat if the coatings fail. Leaks can develop in aging welds. Pumps can fail, meaning the tower can't refill.
And contamination.
Contamination risks too, yeah. From birds, insects, biofilm if hatches aren't sealed properly, and maintaining them is staggeringly expensive.
How expensive are we talking?
Well, a major painting or recoating job, that can run from $500,000 to over $1 million. Cleaning and inspection might be $10,000 to $50,000 every few years. Cathodic protection systems need ongoing upkeep too.
Yikes.
But neglect. That leads to catastrophic failure, which is far, far costlier. These towers are designed to last 50, even 100 years, but only with meticulous ongoing care.
So, okay, these water towers aren't just quirky skyline features at all. They're dynamic, gravity-fed batteries for pressure and supply, demanding constant vigilance, clever engineering, and serious investment.
Exactly right. And speaking of controlling pressure, that leads us to another, usually invisible hero of the system, pressure-reducing valves. PRVs.
PRVs, okay, what do they do?
Their job is simple but vital. Reduce high water pressure from the mains down to safe, usable levels for homes and businesses.
Why is the pressure too high otherwise?
Well, the system needs enough pressure to reach the tops of hills and tall buildings and for firefighting, but that pressure, maybe 150 psi or even more, would burst your home pipes, damage washing machines, water heaters.
Okay, that makes sense. Chaos.
Total chaos.
Yeah.
And lots of wasted water. So PRVs act as guardians of balance. They prevent those dramatic movie-style geysers from erupting in your street, or worse, inside your house. You find them in a couple of key spots. In the city's mains, especially where pipes run downhill from a tower or reservoir, or between zones with different elevations, and very commonly in individual homes or buildings, usually right after the water meter, they knock that high street pressure down to a safe 50-70 psi for your internal plumbing.
And how do they work? Do they need power?
Nope, no electricity needed. They're typically spring-loaded diaphragm valves. Incoming pressure pushes against a diaphragm, and the spring tension is set to allow only the desired lower pressure downstream. They're automatic, self-regulating.
Clever. So they just sit there doing their job.
Pretty much. They mostly work passively. They need periodic inspection, maybe replacement every 10, 15 years, especially in areas with hard water, as scale or wear can cause them to stick or leak.
Okay. From the hidden giants and the hidden valves.
Yeah.
Let's move to something very visible. Fire hydrants. We see them everywhere.
Absolutely. One of the most visible parts.
They're often least understood, I suspect. Beyond just fighting fires, what else are these everyday sentinels actually doing?
Well, their primary job is giving firefighters direct access to that pressurized water main. That's critical. But utilities also use them for other essential tasks. Flushing pipes is a big one, testing pressure in the system, and sometimes providing temporary water access for things like street cleaning or filling construction tankers.
So they're like emergency doors into that hidden network.
That's a great way to put it, yeah. Emergency doors. And something you might have noticed is their colors. Sometimes the whole hydrant is one color, sometimes just the caps on top are different.
Yeah. Why is that? I've always wondered.
It's fascinating, right? It's usually color coding, often based on NFPA standards here in the US, indicating the flow capacity.
Flow capacity. How much water they can provide.
Exactly. The bonnet or caps usually tell the story. Blue generally means really high flow, over 1,500 gallons per minute. Green is good, 1,000 to 1,500. Orange is moderate, 500 to 999. And red means lower flow, under 500 GPM.
So firefighters know instantly what they're dealing with.
Precisely. It lets them quickly assess the available water supply when they arrive at a fire. In many places, the body color can also give info, maybe indicating the water source. Yellow often means public municipal water, while maybe green means it's connected to a private well, or white might be a non-potable or test hydrant.
But that can vary by city.
Right, it can, yeah. Standards like NFPA provide guidance, but local water departments might have their own variations, so firefighters need to know their specific area's code.
That seems like it could get confusing in an emergency if you're moving between areas.
It could add a layer of complexity, which is why consistent training on local standards is so important. Now, about using them. You sometimes see utility crews or maybe landscapers filling trucks from hydrants.
Yeah, is that allowed?
It can be, but only with a special permit and usually a specific meter attached to the hydrant. Otherwise, it's illegal. Opening a hydrant improperly can cause pressure surges or water hammer and potentially damage the system or even contaminate the water.
Okay. And why are there just so many of them? Seems like overkill sometimes.
It might seem that way, but fire codes usually dictate the spacing. Often they require a hydrant every 300 to 500 feet in developed areas.
Why so close?
The goal is to ensure that no building is too far from a water source in an emergency. Shorter hose lays mean faster water on the fire.
Ah, okay, saves time.
Saves critical time. More hydrants generally mean faster firefighting response, which can lead to lower property damage, potentially lower insurance rates for the community, and ultimately safer neighborhoods. And how they work. They tap directly into those large distribution mains underground. The system pressure we talked about pushes the water out at high volume when the valve is opened.
Is there water sitting in the hydrant all the time?
Depends on the climate. In warmer areas, they use wet barrel hydrants, which are always full of water right up to the outlets.
Right.
But in places where it freezes.
Like here?
Like here, yeah. They use dry barrel hydrants. The main valve is actually located deep underground below the frost line. The barrel above ground is normally empty or dry. When you open the hydrant nut on top, it opens that underground valve and water flows up and out. When you close it, the barrel drains automatically to prevent freezing and cracking.
Clever design.
Yeah.
Now, what about when you see crews flushing hydrants, just letting water gush out onto the street for ages? It looks so wasteful.
It does look wasteful, I totally get that, but it's actually crucial preventative maintenance.
How so?
Well, utilities open hydrants fully for a few reasons. One is to clear out any sediment, rust, or mineral buildup that can settle in the water mains over time. Flushing pushes that stuff out.
So it keeps the pipes clean.
Exactly. It also helps maintain disinfectant levels, like chlorine, by pulling fresh treated water through sections of pipe that might have low flow. And importantly, it allows crews to verify the hydrant works correctly and test the available flow and pressure, ensuring it's ready for firefighters if needed.
Okay, so it serves multiple purposes, not just wasting water.
Definitely not. It's essential for maintaining water quality and ensuring the system is reliable for both everyday use and emergencies. Dealing with contamination or a hydrant failure during a fire would be far more wasteful and dangerous. But they do require maintenance. Routine inspections, lubrication, gasket replacements, repainting to prevent rust.
And how much does a hydrant cost?
A new hydrant itself might cost anywhere from $2,000 to $5,000 plus installation. And annual maintenance can be a few $100s per hydrant. Multiply that by the thousands of hydrants in a typical city.
It adds up quickly.
It really does. They're pretty high maintenance assets because they're exposed to weather, traffic, potential vandalism.
Right, collections must be a nightmare.
Oh, absolutely. Vandalism, like opening one without a permit, can cause dangerous pressure drops, water hammer, and even allow contaminants back into the system. And vehicle collisions. You've probably seen the videos. Dramatic geysers, localized flooding, and repairs that can run into the thousands or even tens of thousands of dollars, depending on the damage.
It's incredible, really, how much thought and maintenance goes into something we barely glance at on the sidewalk.
It is.
But, as you said, fire hydrants are just the visible connection, the tip of the iceberg,
Yeah.
connecting to the hidden arteries beneath our streets, the underground piping system.
Yes. Now we're talking about the least visible, but you could argue the most critical part of the entire system, the distribution network itself.
How much piping are we actually talking about underneath us right now?
It's staggering. In the U.S. alone, estimates are over 2.2 million miles of drinking water pipes.
2.2 million miles.
Yep. Enough to circle the Earth.
Wow.
What, about 88 times? Think about that density. There's effectively a buried pipe connecting to almost every single building.
Wow. And installing that must be incredibly expensive.
Phenomenally expensive. Installing just 1 mile of new water main can easily cost anywhere from $1 million to $5 million, sometimes even more, depending on the pipe size, the depth, soil conditions, and especially if it's in a dense urban area versus rural.
So replacing aging pipes, that's a huge challenge for cities.
It's one of the single largest infrastructure expenses municipalities face, absolutely. And these pipes are typically buried, 3 to 8 feet down, deeper in colder climates to get below the frost line and prevent freezing.
Okay. And how does the pressure work within that network? You mentioned towers and pumps.
Right. Pressure is maintained either by gravity from those elevated tanks, the water towers, or by pumps at treatment plants or booster stations within the network. The goal is usually to keep pressure in the range of 40 to 80 psi for most residential areas.
There must be valves down there, too, to control things.
Crucial. Valves, usually gate valves or butterfly valves, are placed throughout the network. They allow crews to isolate specific sections of pipe. If there's a leak or a break, they can shut valves on either side of the damaged section to stop the flow, make repairs, without shutting down water to the entire city.
Like closing off a single street for work.
Exactly. They also use valves to create different pressure zones, especially in hilly cities, to help manage those elevation differences we talked about. Now, maintenance down there, that's tough. Finding leaks in buried pipes isn't easy.
How do they do it? Just wait for water to bubble up.
Sometimes that happens, but ideally they use more proactive methods. Specialized acoustic sensors can actually listen for the sound of water escaping a pressurized pipe.
Listening for leaks.
Yeah, listening for leaks. They also use flow monitoring systems that can detect sudden, unexplained increases in water usage in a specific area, which might indicate a break.
And repairs. Digging up streets.
Often, yes. Repairs are usually expensive and disruptive. Excavation crews dig down to the pipe. Small leaks might get repaired with special clamps or sleeves. Bigger breaks often require cutting out the damaged section and replacing it entirely. Road closures, traffic jams, temporary water shutoffs. It's a major operation.
It's a constant battle then, keeping all that buried infrastructure working.
An ongoing, resource-intensive battle, absolutely.
But let's talk safety. After the water leaves the treatment plant, it travels through all these miles of pipes. Are they truly clean enough for drinking by the time the water reaches our taps?
That's the goal. And generally, yes. Once water is treated, it enters a sealed, pressurized system. That pressure helps keep contaminants out.
Generally. What are the exceptions?
Well, potential issues can arise. Corrosion inside older pipes, especially iron or lead pipes, can leach materials into the water. Biofilm, basically a thin layer of microorganisms, can sometimes grow inside pipes. And if there's a break or a sudden pressure loss, there's a risk of outside contaminants getting in.
So how do utilities manage those risks?
Several ways. Maintaining that disinfectant residual, usually chlorine or chloramine, throughout the system helps kill microbes. Flushing hydrants, like we discussed, clears out sediment and stagnant water. And crucially, actively replacing old pipes, especially lead service lines, and sometimes lining older mains with inert materials helps prevent leaching and improves quality.
And testing. How often do they test the water in the system?
Regularly. Very regularly. Utilities conduct routine sampling at various points throughout the distribution network, designated sampling taps, fire hydrants, sometimes even customer homes.
What are they testing for?
A whole range of things. Microbiological contaminants like E. coli are a top priority. Chemical tests look at disinfectant residuals, pH, lead, copper, nitrates, and other potential contaminants. They also test for turbidity, which is a measure of water clarity.
And there are strict standards.
Absolutely. Agencies like the U.S. EPA set strict legal limits for many contaminants in drinking water. Utilities have to monitor constantly, and if a standard is violated, they're required to notify the public. That's when you might hear about a boil water advisory, for instance. And this brings up an important point. Not all water flowing through pipes underground is the same grade.
Different grades of water.
Yes. We have potable water, which is treated and safe for drinking. That's your tap water. Then there's non-potable water, which isn't treated to drinking standards, maybe used for industrial processes or some irrigation. And increasingly common is reclaimed or reused water. This is wastewater that's been highly treated, not quite to drinking water standards usually, but safe for things like irrigating golf courses, parks, or for industrial cooling.
I think I've heard of that. Doesn't it use different colored pipes?
Often, yes. Reclaimed water systems frequently use distinctive purple pipes. This is super important for identification to prevent accidental cross-connections where non-potable water could get into the drinking water system.
And gray water.
Right, gray water is another category. That's wastewater from sinks, showers, laundry, not toilets. Sometimes it's captured and reused locally, maybe for flushing toilets or landscape irrigation, often with minimal treatment. Keeping all these different grades of water completely separate is absolutely critical for public health.
That idea of keeping things separate, preventing contamination. Brings us to another hidden component, right? Backflow preventers.
Exactly. Another crucial, often overlooked piece, backflow preventers. They are the gatekeepers of clean water, as you put it.
Okay, what exactly is backflow and why is it dangerous?
Backflow is just what it sounds like. The unwanted reversal of flow. Water flowing backward from a property into the public water mains.
How would that even happen?
It usually happens when there's a significant pressure drop in the main line. Maybe a water main breaks nearby, or firefighters open a hydrant, causing a temporary vacuum or siphon effect.
Ah, like sucking water backward.
Precisely. And if that happens, water from inside a building, maybe from a boiler system with chemicals, an irrigation system with fertilizers or pesticides, or even just a hose left submerged in a dirty bucket, could get sucked back into the clean drinking water supply.
That sounds really bad.
It can be incredibly serious. It's a major pathway for contaminants to enter the potable water system and potentially make a lot of people sick. So backflow preventers are mechanical devices designed specifically to stop that reverse flow.
Who needs them? Are they in every house?
Not typically in every single home, although some fixtures have built-in protection. But they are legally required in many situations considered high risk. Think commercial buildings, industrial facilities using chemicals or boilers, hospitals, funeral homes, car washes, buildings with fire sprinkler systems, and very commonly, irrigation systems.
Because those systems might have chemicals or non-potable water in them.
Exactly. The higher the potential hazard or risk of contamination, the more likely a robust backflow preventer is required by plumbing codes. They work using combinations of check valves, which only allow water to flow in one direction, and sometimes pressure differentials and relief valves. One common type is an RPZ, or reduced pressure zone assembly, which is designed to dump water out a relief port if it detects a backflow condition, creating a safe buffer.
Okay. You also mentioned an air gap in the outline. What's that? Is that a device?
Air gap isn't really a device, it's a physical separation. And it's actually the simplest and most reliable form of backflow protection.
How does it work?
It's just an open vertical space between the water outlet, like your faucet, and the highest possible water level in the fixture it's discharging into, like the flood rim of your sink.
Ah, so the faucet spout being above the edge of the sink.
Exactly. That physical gap makes it impossible for dirty sink water to siphon back up into the faucet and contaminate the water line. Same principle for a toilet fill valve being above the tank's water level, or a dishwasher drain looping up high before connecting to the plumbing. It's basic physics, but legally required for safety.
Simple but effective.
The best kind of safety feature. Now, for those mechanical backflow preventers, especially in commercial or industrial settings, they don't just get installed and forgotten.
They need maintenance too.
Yes, and testing. Most jurisdictions legally require them to be tested annually by a certified backflow tester. Typically, yes. These testers check that the internal check valves are sealing properly and the relief valves are working. They replace worn parts and file official reports with the water utility or health department. Failure to keep up with testing can lead to fines or even the water service being shut off to the property.
So it's a serious legal obligation.
Very serious. And the consequences if one fails? Well, like we said, contaminants, fertilizers, pesticides, industrial chemicals, sewage, pathogens could potentially enter the public drinking water system. A single backflow incident can impact an entire neighborhood, cause serious illnesses, and trigger massive, costly emergency flushing procedures by the utility.
Wow. It really is like the immune system of the water network, isn't it? Constantly working behind the scenes to protect us from invaders we rarely even consider.
That's a perfect analogy, an immune system. And thinking about that system-wide protection leads us to some of the larger design philosophies that make the whole network function, making it incredibly resilient in some ways, but also highlighting its vulnerabilities.
Like what kind of design philosophies?
Well, for instance, redundancy and loops. Water distribution systems usually aren't designed like a tree, with single lines branching out. They're often designed as interconnected looped networks.
Why loops?
Resilience through redundancy. It means water can reach any given point from multiple directions. If there's a break in one pipe, crews can isolate that break. But water can often be rerouted through other parts of the loop to keep supplying customers downstream. It minimizes service interruptions.
Smart. Keeps the water flowing.
Exactly. Another key design principle is zoning based on elevation. Cities aren't flat, right?
Definitely not.
So they divide the distribution system into different pressure zones. This ensures relatively consistent pressure for everyone. Houses way uphill might need a booster pump station to get enough pressure, while houses way downhill might need those PRVs we talked about to reduce pressure and prevent pipe bursts.
So everyone gets usable pressure, regardless of where they live.
That's the goal. Without careful zoning, people uphill might get a trickle, and people downhill might have their plumbing blow apart. And connecting all this, increasingly, is technology. Modern systems are becoming digital organisms thanks to those SCADA systems we mentioned earlier.
The row monitoring.
Right. Digital sensors constantly monitor flow rates, pressure levels, water quality parameters like chlorine residual, tank levels, all in real time. Operators in a central control room can see the entire system at a glance.
What can they do remotely?
They can often detect leaks much faster by spotting unusual flow patterns. They can remotely adjust valve settings to reroute water or manage pressure. They can turn pumps on or off. It makes the system much more responsive, efficient, and easier to manage proactively.
But even with all this tech, there's the challenge of age, right?
Yeah.
You mentioned old pipes earlier.
That's the huge elephant in the room. Aging infrastructure. Much of the water network in the U.S. and many developed countries was built 50, 70, even 100 years ago or more.
100 years. Are there really pipes that old still in service?
Absolutely. Some cities even still have some wooden water mains buried underground from the 19th century, believe it or not. Though most are cast iron, ductile iron, concrete, or increasingly plastic now.
Wow. Wooden pipes.
And these old pipes, especially metal ones, are nearing or past the end of their designed lifespan. They corrode, they become brittle, they break more easily. Leaks and breaks are a massive problem, wasting billions of gallons of treated water every single day worldwide.
And replacing them is that huge cost you mentioned.
Staggeringly expensive, yes. The American Society of Civil Engineers consistently gives U.S. drinking water infrastructure a poor grade, like a C or D plus FA. The EPA estimated recently that over $470 billion is needed just for drinking water infrastructure upgrades over the next 20 years. It's a massive funding challenge.
Okay, other design considerations. You mentioned cross-connection control.
Right. That ties back to keeping different water grades separate. Preventing any accidental physical connection between the potable water system and any non-potable source, be it reclaimed water, industrial process water, or even a well. Those purple pipes for reclaimed water are a key part of that control.
Makes sense.
Another big factor is designing for fire flow versus just domestic demand. Meaning the system often has to be sized much larger than what's needed just for people to drink, shower, and water lawns. The pipes, pumps, and storage need to be able to deliver the huge volumes of water required for firefighting. In many cases, fire protection requirements actually dictate the minimum pipe sizes in the network.
So fire safety drives a lot of the design and cost.
A significant amount, yes. We also can't forget the energy-water nexus.
The link between energy and water.
Yeah, it takes a lot of energy to pump water from its source, treat it, and then pump it all through that vast distribution network. Globally, estimates suggest somewhere around 7 to 10% of all electricity generated goes towards water supply and wastewater treatment.
Wow, that's a huge chunk of energy.
It is. And conversely, many power plants, especially thermal ones, require vast amounts of water for cooling. So water and energy systems are deeply interconnected and interdependent. And finally, thinking about resilience. Beyond loops and zones, there's emergency preparedness. Backup generators at critical pumping stations and treatment plants are vital. Water towers and reservoirs provide that crucial buffer, maybe hours or even a day or two of supply if everything else fails.
But major disasters can still overwhelm the system.
Oh, absolutely. In big disasters like major earthquakes, hurricanes, or floods, water systems are often among the first critical infrastructure systems to fail. Broken mains, contaminated supplies, power loss. Restoring safe drinking water is always one of the highest priorities in any disaster recovery effort.
So, okay, taking all this in, what does it all mean for us, really? From those silent water towers on the horizon to the hydrants on our corners, the valves we never see, and those millions of miles of pipes hidden beneath our feet. This water system is truly the unseen, incredibly intricate engine of modern life.
It really is. Complex, definitely aging in many places, and maybe surprisingly fragile when you think about all the points of potential failure.
Yeah.
You know, the water system is fundamentally a trust system. It's invisible for the most part, buried, definitely unglamorous work. Yet we put our complete faith in it every single day.
That's true. You never doubt it will work.
It's like civilization's hidden contract, isn't it? We build and maintain these pipes and pumps, often at huge expense, and in return, we expect clean, safe water to flow every single time we turn the tap.
And this deep dive really reveals that every single glass of water you drink is proof of this hidden network functioning exactly as it's supposed to. It safeguards our health, it fuels emergency response, it makes that simple, everyday miracle of turning on a faucet possible.
But it's also a stark reminder, I think, that the ongoing vigilance, the investment, the sheer respect for this vital infrastructure,
Yep.
it's paramount. Because when any significant part of the system fails due to age, disaster, neglect, contamination, the consequences can be truly profound, impacting the health, safety, and economy of an entire community.
Absolutely. Definitely something for you, our listener, to ponder next time you turn on your faucet or see a water tower on the skyline. What responsibility do we all share in understanding and protecting this incredible invisible system that sustains us? And maybe, what does its future look like in a world facing increasing water demands and the undeniable reality of aging pipes?